Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE, and BIT SAT. He has more than 16 years' experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series in BSc Honours in Physics. We have been listening to a series of lectures on the topic electricity and magnetism. In today's lecture, we are going to learn about the concepts related to magnetism. Before we start this lecture, let us see the session outline for today's lecture. In this lecture, we are going to see the classification of magnetic materials, under which the categorization, namely diamagnetism, paramagnetism, ferromagnetism, we are going to learn. And finally, a property called magnetic hysteresis exhibited by ferromagnetic materials. All this we are going to see in this lecture. On what basis we classify them into dia, para, and ferromagnetic materials? It is mainly based on the values of relative permeability and the magnetic susceptibility. Shall we have a look at the way in which these values vary for these magnetic materials? Based on the values of the susceptibility and the relative permeability, the magnetic materials can be classified into the following three types. For diamagnetic materials, the magnetic susceptibility is a low negative value and relative permeability is slightly less than 1. And for paramagnetic materials, susceptibility is a low positive value and relative permeability is slightly greater than 1. And for ferromagnetic materials, susceptibility is a very high positive value and the relative permeability is very much greater than 1. So, on these basis we have classified the materials. The susceptibility is a negative value for diamagnetic materials. Actually, when a diamagnetic material is kept in external magnetic field, it magnetizes in the opposite direction. Normally, the dipole moments have to align in the direction of external magnetic field. But as far as the diamagnetic materials are concerned, the magnetization is happening in the opposite direction. That has to be understood properly. For para and ferromagnetic materials, the alignment takes place very easily. That is why they have the mu r value as a higher value, and susceptibility is also a positive value. And for ferromagnetic material, it is very high. That means the alignment is very strong. But for diamagnetic materials, it is happening the other way. We need to find out the reason. How the alignment is happening in the opposite direction? Is it not the violation? So, here is the explanation for it. As far as the diamagnetic material is concerned, they normally have the paired electron configuration, the even number of electrons. And as per the model of atom, the atomic model, when there are paired electrons, they have to orbit around the nucleus in the opposite direction. So in that case, they don't have net magnetic moment. The magnetic moment produced by one circulating electron is cancelled by the other. In one of the earlier lectures, when we tabulated the susceptibility value for helium and neon, they have even number of electrons. That means the paired electron system. The susceptibility was reported as 0. They don't have any susceptibility. And as far as these diamagnetic materials, so they are also diamagnetic in nature. These diamagnetic materials are concerned, when it is subjected to external magnetic field, what happens? I hope a kind of visualization will enhance your understanding as far as these diamagnetic materials are concerned. So let us take up this case in the diamagnetic system. There is one electron revolving around, but in the diamagnetic materials there are paired electrons. There is one more electron revolving that I wanted to show you. This is how it is revolving, and its direction is opposite to that of the already existing one, which is shown. So that has the magnetic dipole moment or the magnetization produced in this direction. So the net magnetization is 0 or magnetic moment is 0. What is magnetization? It is magnetic moment per unit volume. All these relations are familiar to us. This is before it is subjected to the external field. This cancels this one. They both are equal in magnitude, opposite in direction. But once it is subjected to external magnetic field, what happens? The one which was revolving in this sense is increasing in angular frequency. That means it rotates faster. What about the one I have shown you? So this orbiting electron is actually slowing down. Because it is slowing down, comparing to this magnitude, it is slightly less than that of this length. So what happens? The net magnetic moment is in the opposite direction to that of the applied field. So this is how it gets magnetized in the opposite direction. Having understood the concept, now let us see some of the properties. What is the diamagnetic materials going to have? As I have already stated, some of the highlighted points I would like to show here. Diamagnetic substances are those in which net magnetic moment of the atoms is 0 because they cancel, one will cancel the other. When the external magnetic field is applied, a weak magnetic moment is induced in the opposite direction. This causes the diamagnetic substances to be weakly repelled by the magnet. The reasons I have explained. Diamagnetism is present in all matter. Its effects are much smaller than those of paramagnetism or ferromagnetism and are evident only when those other effects do not exist. The diamagnetic nature is found in all materials, but in para and ferromagnetic materials, the diamagnetism is suppressed. If the para and ferromagnetic effects are not there, then the diamagnetism is exhibited, and that too it is mild. The only significant thing is it is in the opposite direction. We have also learned the reason. Now let us see the properties of diamagnetism. The susceptibility has low negative value. For example, bismuth has a susceptibility of minus 0.00017. It is a low negative value. The susceptibility is independent of temperature. The relative permeability is slightly less than 1. When placed in a non-uniform magnetic field, they have a tendency to move away from the field, that is from the stronger part to the weaker part of the field. So these are the following effects. Because it is getting magnetized in the opposite direction, all these properties are found in the diamagnetic material. And one more highlighted information is, it is independent of temperature. Temperature cannot alter the magnetization that is happening in diamagnetic material. Normally, the magnetism is affected by the temperature. When temperature increases, the alignment is slightly getting disturbed because it will cause the thermal vibration. But as far as the diamagnetic materials are concerned, it is not due to the alignment, it is not due to anything, it is due to the speed of rotation of the electron. When the magnetic field is applied, one rotation is enhanced, which is in the opposite direction to the applied field, and the one which is suppressed, the speed is reduced, that is in the direction of the external magnetic field. So thus it is independent of temperature. The thermal vibrations cannot significantly alter the magnetic property of diamagnetic material. What are the other points we have? Let us continue. They get magnetized in the direction opposite to the field. When suspended freely in a uniform magnetic field, they set themselves perpendicular to the direction of the magnetic field. And I have given you some of the examples of the diamagnetic materials. And this is how the alignment happens when a diamagnetic specimen is kept in the external magnetic field. It aligns in the perpendicular direction. It is already magnetized, so it gets magnetized, it aligns in the perpendicular direction. And here there is a diagram which shows this is a diamagnetic material and we have a magnetic field producing thing. It is repelled, so that produces a kind of levitation. How do we make a diamagnetic material? We can reduce the temperature to a very low value, thus the diamagnetic nature would be exhibited. When materials are brought to the superconducting state, they exhibit the diamagnetic behavior, that is called the Meissner effect. So all these come under the diamagnetic nature of materials. It is only when the temperature is reduced to a very low value, that means it has to be brought to the superconducting state, which is altogether a different state, the diamagnetism is exhibited in the materials. Shall we now take up the paramagnetic materials for our study? We will do that. Paramagnetic substances have a small permanent magnetic moments, resulting a small but positive magnetic susceptibility. Here, this is due to the alignment. They already have permanent dipoles existing in the material, so they have a lone electron revolving. It does not have a paired system. In diamagnetic only it is the paired system, but here they have permanent dipole moments. When subjected to external magnetic field, they have to align. That's what is happening. These moments interact only weakly with each other and are randomly oriented in the absence of an external magnetic field. Why it is mentioned like that? Why they don't have magnetism initially? Because these tiny magnetic moments are aligned in different directions. Because of thermal vibration, because they are existing in different directions, it is like that. So net magnetic moment is not there, so no magnetism is found before it is magnetized. And another important thing is, as far as the paramagnetic materials are concerned, the one alignment will not affect the other because they are not interacting with each other. Each alignment will be in different directions. One cannot influence the other. But in ferro, such an influence will happen. Let us discuss it when we take up ferromagnetic material for discussion. But here it is randomly oriented. When a paramagnetic substance is placed in an external magnetic field, the alignment process competes with the thermal motion, which tends to randomize the magnetic moment orientation. So here what do we understand? The temperature effects will be there. When temperature changes, the magnetic property will be altered because it depends on the alignment. Temperature will affect the alignment. That is the reason. Let us see the properties of paramagnetic materials. As far as the susceptibility is concerned, it has a low positive value. For example, in the case of aluminum, susceptibility is a positive value. It is 0.00002, very low value, but it is positive, that we have to notice. Susceptibility is inversely proportional to absolute temperature. Here there is a relation shown. Susceptibility is inversely proportional. The temperature appears in the denominator. The numerator we have C. This C is called Curie constant. This law itself is called Curie's law. This relationship is called Curie's relationship. The relative permeability is greater than 1. When placed in a non-uniform magnetic field, they have a tendency to move from weaker part to the stronger part. This behavior is totally different from the diamagnetic. Diamagnetic moves from stronger part to weaker part, but paramagnetic moves from weaker part to stronger part. This is again based on the way in which they get magnetized. What are the other points? They get magnetized in the direction of the field when it is subjected to external magnetic field. When suspended freely in a uniform magnetic field, they set themselves parallel to the direction of the magnetic field. This is how they align. Whereas diamagnetic perpendicular, but here they align parallel to the magnetic field. And these are some of the examples for the paramagnetic materials. Now we will take up the ferromagnetic materials for our study. Here also we will discuss about the susceptibility and relative permeability, all that. A small number of crystalline substances in which the atoms have permanent magnetic moments exhibit strong magnetic effects called ferromagnetism. All ferromagnetic materials are made up of microscopic regions called domains, regions within which all magnetic moments are aligned due to spin exchange interaction. Here there is a diagram showing how they are forming the domains. You would like to know more about domains? So we will discuss about the domains and then come back to the illustration. In the case of paramagnetic materials, there is no interaction between the neighboring dipoles, magnetic dipoles. They just align randomly. The thermal effect is also there. But as far as these ferromagnetic materials are concerned, there is a spin attached to the orbital movement that has a stronger effect. So that will influence the neighboring dipoles, and if they are oriented in different direction, that is also made to align in the same direction. So thus there is a region. That region is only called a domain. That region will have one particular direction. Now look at this illustration. There are different regions. Hope these white color separations you are able to notice in this illustration. In each domain the directions are different before it is magnetized. When the external magnetic field is applied, what happens? The alignment happens. But when the alignment is there, when we remove this magnetism, this external magnetic field, this alignment will continue. This will not easily get disturbed. Even by thermal means and all that, the alignment is going to be permanently existing because of the spin exchange interaction. And what about the domain? Because already the domains are formed, it is enough for the external magnetic field to make these domain magnetic dipole moments to be in line with the externally applied field. So that is how the magnetization is enhanced in the case of ferromagnetic materials. You would like to know much about the domain formation and all that, what would be the size, how many atoms are there in the domain. These are the information I would like to share with you. All ferromagnetic materials are made up of microscopic regions called domains. The regions within which all magnetic moments are aligned, these domains have volumes of about 10 to the power minus 12 to 10 to the power minus 8 meter cube, that means very small, and contain about 10 to the power 17 to 10 to the power 21 number of atoms. Once the moments are aligned, the substance remains magnetized after the external magnetic field is removed. This permanent alignment is due to the strong coupling between the neighboring moments, a coupling that can be understood only in quantum mechanical terms. But right now the alignment will exist. That is the point that we have to keep in mind. We will see some of the properties of the ferromagnetic materials. The susceptibility and relative permeability are very large values. For example, the mu r for iron is nearly 200,000. So this is a huge value with which the iron is existing. Susceptibility is inversely proportional to the absolute temperature. At a particular temperature, the ferromagnetism becomes paramagnetism. This transition temperature is called Curie temperature. For example, for iron, the Curie temperature is about 1000 Kelvin. Why the ferromagnetic material is changed into paramagnetic material? We have seen there is a permanent alignment even in the absence of the external magnetic field once it is magnetized. What can affect this magnetization, this alignment? Only the thermal vibrations can affect. So when the material is subjected to high temperature, at a particular temperature, this rigid parallelism in the alignment is affected. That means the spin exchange interaction is cut off. Thus the magnetism is destroyed, and maybe it would become a paramagnetic material in which the magnetization is happening but with a lesser effects, not that strong. So that temperature at which the transition from ferro to para happening is called Curie temperature. Let us have a look at this graph. This shows how the transition is happening at a temperature called Curie temperature from ferromagnetic to paramagnetic. So this is the magnetization, and here we have the temperature. It has this kind of trend. Within the domain, within the curve, it is behaving as a ferromagnetic material. Outside, it is behaving as a paramagnetic because it has come beyond the Curie temperature. And what are the other points, other properties? When suspended freely in uniform magnetic field, they set themselves parallel to the direction of magnetic field. When placed in a non-uniform magnetic field, they have a tendency to move from weaker part to the stronger part of the field. They get strongly magnetized in the direction of the field. Example for the ferromagnetic materials are given. It is iron, nickel and cobalt, and number of the alloy materials of these compounds. they also are found to be ferromagnetic in nature. So, the ferromagnetism is a peculiar material which retains the magnetism in it. When such ferromagnetic materials are subjected to magnetization cycle, that means a virgin material which is not magnetized but ferromagnetic in nature, how the magnetization would happen? That itself is called the magnetization cycle. These ferromagnetic materials possess a peculiar property called hysteresis, magnetic hysteresis. So, with a diagram, this could be easily understood. I would like to show a graph of the magnetization cycle to explain what is magnetic hysteresis. The word hysteresis literally means lagging behind, which is seen that the magnetic induction B lagging behind the magnetizing field H in a cycle of magnetization for the ferromagnetic materials. This phenomenon of lagging of magnetic induction behind the magnetizing field is called hysteresis. Hysteresis is a closed loop over a magnetization cycle. Here the diagram is shown. The material takes this path when it is virgin, not subjected to the field. Here we have the magnetizing field. Here the magnetic induction that is produced, and it starts from 0, 0 and reaches a saturation, and after that it is not following the same path, it takes some other path. So, this kind of behavior is called magnetic hysteresis. It remembers the way in which it got magnetized. It does not lose the memory of it. So, that is why this material is magnetically hysteric. So, the name hysteresis comes into the picture. There are lots of applications based on the hysteresis property of ferromagnetic materials. We will learn about all of them in the upcoming lectures. Hope I have come to the end of today's lecture. Shall we see the summary of today's lecture? In this session, we have seen the concepts of classification of magnetic materials, the diamagnetism, paramagnetism and ferromagnetism that are present in different magnetic materials. And also we have seen a peculiar property called magnetic hysteresis property exhibited by ferromagnetic materials. Before we wind up this lecture, we will see the questions of today's lecture and test our understanding of the concepts. Discuss the reason and characteristics of dia, para and ferromagnetism in materials. What is Curie law and the Curie temperature? What are domains in ferromagnetic materials, and what is the reason for the formation of domains? Explain the magnetic hysteresis of ferromagnetic materials. With this, I would like to conclude today's lecture. See you in other lectures with the concepts related to magnetic hysteresis and the applications of ferromagnetic materials. Thank you for watching this program.